Nope. Doesn't seem like there's a whole lot of notes today, only 5 pages. Okay, well, may as well jump in. So at the end of last time, we were talking about waves, and actually, let me pull up notes from the end of last time just to refresh. We were talking about standing waves, and there's this whole business of energy and all of those things, but so far we haven't really talked about any useful applications of standing waves or why we care about them at all. So we're actually going to introduce, we're not quite going to get there, but we're going to introduce the machinery and the mathematics we need today in order to talk about standing waves in a useful manner. By the way, note that the standing wave discussion is relevant for example, question 4 on the homework. This is that business regarding the guitar. That's how guitars produce notes. They produce standing waves. Right, so today we're going to talk about sound. Oh, there we go. So the first question to ask is, what is sound? Now you guys have all heard sound being described as sound waves, and you're right, sound is produced, or is a type of wave. It's a type of wave in air in particular. Well, at least the sound that we hear. But we can do better than that. We now have some of the language that we need in order to describe sound adequately. In particular, sound is a longitudinal wave. Hopefully you guys remember, a longitudinal wave is a wave where the directional gradient, that is the direction in which this thing changes, is in the direction of propagation. Here, for sound, we have compressions and rarefactions. Now, you guys probably all know the word compressions. You might not know the word rarefactions, or there's no R there. Rarefactions. Rarefactions are just the opposite of compressions. So when we talk about compressions with regards to sound, we're talking about that the air molecules are close together. And when we talk about rarefactions, we mean that the air molecules are far. So all that's happening in a sound wave is that you have regions of high density of air. These are compressions. And then, so that would be like at the peak of the wave. And then you have rarefactions at the troughs of the wave. And those compressions and rarefactions just travel in space. Sound, in fact, can propagate through any medium. Well, through any matter. But we typically use air, because we breathe air and that's what we exist in. But, you know, sound does travel through water, sound travels through metals, a whole bunch of different things. However, it is important to note that the way sound propagates through solids and liquids is genuinely distinct from the way it travels through gases. So in space, there is no medium for the sound to travel through, which is the issue. That's why we say that there is no sound in space. That's why I said it can propagate through any matter. You need matter to be there in order to have the sound wave. Now, the reason we care about sound is because it's one of the ways that we experience the world around us. So how does that work? Well, hearing, this sense that we have, detects pressure changes by those pressure changes causing the eardrum to vibrate. So a pressure change, you have some amount of pressure on the inside of your eardrum. When the pressure on the outside of your eardrum is higher, it pushes in on your eardrum. When it's lower, it pulls out on your eardrum. And so when the pressure wave, when the compression is near your eardrum, you have higher pressure, so it pushes your eardrum in. When you have a rarefaction, you have a lower pressure, so it pulls the eardrum out. And so this oscillation of the eardrum is what we hear. In fact, it's transmitted through the 3 bones in your ear, and then those are connected to the inner ear, which has all of the hairs and the fluid, which then are detected by the hair cells. and that is the extent of my biology knowledge. But that's how we hear. We hear by detecting these changes in pressure waves, and that's why the eardrum is so important. If you puncture it, then there is no pressure differential, and hence your eardrum won't move and you won't be able to hear, which would be bad. Now, there are two ways, I don't know why I'm so sniffly this morning, must be allergies. There are two ways to describe the disturbance of a sound wave. So remember that a wave is just a disturbance that propagates. And so in a lot of cases, there's just one way to describe it. Like on a string, the disturbance is just vertical displacement, right? But for a sound wave, we can describe it in two ways. Sometimes one method of description is more useful than the other. So the first method that might seem the most obvious is the average. I'm putting average in parentheses because we can't really compute. Since vacuum doesn't have matter, sound can't propagate through it, right? Yeah, that's precisely it, yeah. That's why there's no sound in space, and in space, no one can hear you scream, right? Because there's just nothing to propagate the sound. Right, so one of the ways to describe the disturbance is the average particle distance from mean position. And I'll describe what I mean by this in a minute. The second way, which turns out to be more useful, is we compute the local pressure difference from 1 atmosphere. ATM is the abbreviation for atmosphere. So you can imagine that these two things would be related, right? If you have air molecules moving back and forth on average, then occasionally, sometimes a lot of air molecules will be closer together and you'll have a higher pressure difference. And other times you'll have a lot of air molecules further apart and you'll have a lower pressure, or you'll have a negative pressure difference. You'll have a lower average pressure than atmospheric pressure. And so these are related. However, this means of describing it, talking about pressure differences, is way more useful because in reality, the air molecules themselves aren't actually oscillating, right? They're just bouncing around and doing their thing. It's just on average they look like they oscillate. So if you took like some sort of weighted average, then you could adequately describe these in terms of particle distance from where the particle wants to be, but it's not a particularly useful way of describing the wave. So let me show you the GIF again. Let me pull it up. Is it this one? Yeah. So let me share it. So I showed you this before. But so what I want you to do is I want you to take a look at the say this middle red dot, right? So it has an average position, right? It's somewhere in the middle between the two ends of its oscillation. So when it is at its maximum oscillation, what is the pressure at that location? Well, it's somewhere between its minimum pressure and the maximum pressure, right? It turns out that on average, the maximum average displacement occurs precisely when the pressure is 0. Or sorry, when the pressure differential is 0, i.e. when the local pressure is atmospheric pressure. And the minimum, and the displacement is 0 when the local pressure is at a maximum and when it's at a minimum. So I can describe that in words to you a little bit better. Hopefully you guys can, I wish that there was a way that I could share both things with you. Advanced? No, it doesn't work. Okay, well, let's go back to the lecture. So we want to talk about how the oscillation of the particles relates to the pressure differences. So as hopefully you guys saw, they are not in phase with each other, i.e. the point of maximum oscillation, the point and time of maximum oscillation, is not the same point in space and moment in time where you have maximum pressure differential. That means that they are not in phase with each other. i.e. if you were to try to plot them both together as like sine waves, one would be like this and the other one would be like this. They don't overlap perfectly. And to be more specific about them not being in phase with each other, we saw that the maximum displacement, this is the displacement, the average displacement of an air particle, occurs when we are at equilibrium pressure. It occurred halfway between minimum and maximum pressure, and vice versa. So minimum displacement also occurs at, minimum displacement occurs at maximum or minimum pressure. So this means that they're kind of like a quarter of a wavelength or a quarter of a cycle out of phase, because if it was that when one was maximum, the other was minimum, i.e. if it was like this, then they would be precisely pi radians out of phase, right? We talked about this phase constant that tells you where you start. So in this case, this one is, say, just sine of x. This one would be sine of x plus pi, or x minus pi, depending. However, if instead we started with, let's say that this is our displacement, that would be sine of x, we see that the pressure is the pressure is maximum when the displacement is let me make sure I get this right. The pressure is maximum when the displacement is going down and it's at equilibrium. So that would be something like this. So here we have sine of x. Here we would have pressure. And by the way, if you look carefully at that diagram, you could actually see this. But for now, just believe me. Actually, you know what? I'm going to redraw this just because it's a little bit easier to see. So let's start by drawing the pressure diagram first. This is a normal sine, normal sine wave. And the reason I'm drawing this one first is because it turns out that pressure leads displacement, so it'll be a little bit easier to see. Then the displacement would look like this. Oh, okay, I need to get this right because they have the same wavelength. Like that. There we go. Yes, I'll do it in color. That's a good idea. Okay, how about this? Something like that. I do my best. I'm no artist. Sorry. Yeah, I'll label them. This is displacement. I just go back to black ink or black color. This is pressure. Here we go. All right. Yeah. Sorry for the delay. So if this is just a sine of x, and so now hopefully you can go and you can look. You can look that when the pressure is at a maximum, the displacement is going to the left in the picture that or in the GIF that I showed you before. When the pressure is at equilibrium, it is furthest to the left. When the pressure is going down and it's at equilibrium, it is furthest to the left. So this displacement, if this is sine of x that I've drawn here, what would this one be? Well, this one would be sine of, well, we know it has to be a quarter of a wavelength, or a quarter of a cycle, which is pi over 2. Which way is it? Well, we want to shift it to the right. Sorry, shift it to the left. So we have to add pi over 2. Now, obviously, there's going to be, it's not quite that simple. It'll actually be, you know, sine of kx plus omega t plus pi over 2, and so on. You know, there's going to be other terms. But the point that I'm getting at is that there is this phase constant of pi over 2 relative to the phase constant of the pressure wave. This is this whole business of leading, of two waves being out of phase. One wave will lead another, and so we would talk about the phase constant. In this case, displacement is pi/2 radians out of phase. And we can also see that pressure, this is just language that you'll see, that you'll want to learn about if you're some sort of electrical engineer. Pressure leads displacement. So when you're doing electrical engineering, you might say something like current leads voltage, or voltage leads current, and that's what it means. It means that is the one that is in front when it comes to drawing a wave diagram. Now, why does this happen? Well, think about what is causing the displacement to occur. Well, we know that particles won't move unless a force acts on them, right? Fortunately, pressure is force over area. So it turns out that the restoring force that causes the displacement, oh, I'm running out of space, comes from the pressure difference. So a change in pressure will lead to an acceleration of the particle, but it won't lead directly to the particle's position being different automatically. So the pressure difference will come first, and then the particle will accelerate and move to a new location. So that's why you have that the pressure leads the displacement, because the pressure is causing the change in displacement. Hopefully that makes sense. It seems relatively intuitive to me. And you can make this formal mathematically if you wanted to, but it's enough to just use your intuition here. Right, so hopefully we know what sound waves are now, right? Sound waves are either pressure waves or displacement waves for particles longitudinally. We're just going to talk about it in terms of pressure waves. It's the simplest that way, that's the way most people do it. So now we can actually talk about sound wave, or properties of sound waves. These are things like speed and so on. So the sound wave velocity, is my video still, oh, my video disconnected. Oh, bummer. Sound wave velocity, or the sound wave speed, at standard temperature and pressure, which is STP, that's what it means, standard temperature and pressure, has a value. There just is a speed of sound at atmospheric pressure and like 20 degrees Celsius or something. And it is 344 meters per second. Just is what it is. Now, do notice that this depends on the medium. Just like how the speed in the wave speed in a string depends on the medium, the tension and the linear mass density, the speed of sound depends on what medium that sound is traveling through. For fluids, liquids and gases, the speed of sound, say Vs, is given by the formula B divided by rho, where B is the bulk modulus. Don't actually ask me what that is, because that's an engineering thing that I don't really know much about. All I know is that it's basically the same thing as tension. And rho is the density of the medium. Bulk modulus is basically how sticky is the stuff to itself. And it's used for fluids. For solids, on the other hand, because sound can travel through solids, it ought to be able to, otherwise like somebody shouldn't be able to hear me on the other side of the room. Sorry, on the other side of the wall. The speed of sound is given by a similar formula. It's just y divided by rho, where y is Young's modulus, which is a similar thing as the bulk modulus, but just for solids. It's just, again, it's just a measure of how sticky and how strong the force is between molecules. And again, rho is the density. So remember, this is a lot like for a wave on a string. For a wave on a string, it was square root of the tension force divided by the linear mass density. So for a string is one-dimensional. So it's only going to have a linear mass density. It doesn't really make sense to talk about its overall density. And it has some stickiness thing that tells you how hard each part of the string is tugging on each other part. So the analogy here is that the moduli are like the tension, and the density is like the linear mass density. And then the formula is the same, which is kind of, perhaps it's surprising, right? But it's really not, and it's just because of the way that waves travel. They are a result of a restorative force, and so they're all going to have very similar properties. Now, we can also talk about intensity. So, for a, and I want to make sure I get this right because my notes don't seem quite, yeah, okay, that's right. The intensity of a sound wave is 1/2 rho b times omega squared times the displacement amplitude squared, or it can be rewritten as the pressure amplitude squared divided by 2 times the square root of rho times b. This is, again, in a fluid. So let me put a box around this just so then you know it's important later. I'm using the formulas with the Boltzmann mod. Yeah. I would, unless I'm giving you everything else and saying, hey, the wave speed is such and such, calculate the bulk modulus. Yeah, no, I'll give you those because those are hard to calculate from first principles. Like that's something that requires, a graduate degree and years of experience. Like it's not something that's trivial. Just so there are two ways that you can write the intensity, and that's because you can describe the wave either in terms of a displacement wave or in terms of a pressure wave, a longitudinal displacement wave anyway. Note that it's not actually a displacement wave, but we're just abusing the language there because it's not actually just a particle oscillating back and forth. So the reason why I gave you the formula for the intensity for using the quote-unquote displacement formalism is just to remind you of what the intensity looks like for a string. For a string, it's 1/2 mu f times omega squared a squared. So we could have guessed this formula from a string. Basically the same formula for the intensity. You just replace mu with rho and f with b, just as we did in the velocity. But that's the only difference. However, it's not a particularly useful formula because it's very, very hard to measure the physical displacement given a sound wave. You can measure the pressure, that's pretty easy. You just get a pressure meter or a barometer. But measuring the displacement is hard. However, in both cases, it's proportional to the amplitude squared. You might need more information with regards to for the displacement type calculation. So we're going to use the bottom one more frequently than the top one, especially because it doesn't depend on the frequency, which is interesting. Interesting and useful anyway. But I just wanted to show you both so you can see them both. Right. So we have a formula for intensity, but I've left something out because, right, we hear sounds, but the loudness of a sound is not the same as the intensity of the sound. It's just a fact of how our ears work. Sorry, I'm going to sneeze. Oh. No, don't sneeze it. I will be right back. Sorry, my allergies that don't exist. No, I should be here. My allergies that don't exist just decided, I don't know, make my nose very itchy and runny and whatever. I promise I don't have allergies. At least I never did as a kid. Maybe I developed them when I moved to Davis. Anyway, right, so we don't actually hear intensity, right? The volume of a sound is not just its intensity. It doesn't work. It could be. But I've never, I'll think about that. Anyway, right, so we don't hear intensity. We hear something else. So we have to introduce a new concept called the decibel. Right, so there is, so intensity does characterize something about how strong the sound is. So it seems reasonable to say that you could measure the minimum intensity that a human could hear. And in fact, that was done. The minimum intensity for human hearing, this is an average, of course. We call it I0, and it is 10 to the minus 12, which is a very, very small number, watts per cubic meter. Sorry, watts per square meter. That is, so it turns out that if you were to produce a sound that has an intensity of 10 to the minus 12 watts per square meter, remember, intensity is power divided by area for a three-dimensional wave, and sounds are three-dimensional waves. So watts per square meter works. If you produced a sound with that small intensity, you could just barely hear it. It's like a pin dropping from across the room kind of thing in a silent room. Similarly, we know that very, very loud sounds hurt, right? Like sufficiently loud sounds, if you're next to like a jackhammer or something, that will hurt your head, hurt your ears. And so we can also measure the threshold for pain in terms of intensity. So by the way, what we're doing is we're producing two fixed points to calculate the volume that we hear by producing reference points. So the threshold for pain, it's about 1 watt per square meter. Now notice, these are 12 orders of magnitude apart from each other. So it doesn't make sense to just say, okay, well, how loud is it? Well, it's 6 times 10 to the minus 12 watts, or 6 times 10 to the minus 9 watts per square meter. It's not a very useful thing, because it's not like something that hurts sounds a trillion times louder than the quietest thing you can hear, right? It's like maybe 100 times louder or 1,000 times louder, but it doesn't sound like it's a trillion times louder. Similarly, two things that have a difference of intensity, like say a conversation and a loud conversation, a difference of intensity of maybe a factor of 10, maybe they sound like twice as loud. So because there's this huge order of magnitude in the range of things we can hear, it's not a sensible way to characterize the volume that we hear something at just in terms of intensity. We need a logarithmic scale to compress the scale. I.e., we want to be able to say that there is a small, that the range, you guys know what logarithmic scales do. I'm not going to talk too much about that. So what we're going to do for this logarithmic scale is we're going to use I0 as a reference intensity. And so what we do is we say, we write a formula. Beta, which is just going to be the formula for decibels, or it's the letter for decibels, is 10 decibels. By the way, a decibel is just 10, or is 1/10 of a bell, but we don't use the bell for some reason. It's 10 decibels times log base 10, the one and only time you'll use log base 10 ever, of the intensity divided by the reference intensity. Now let's look at this formula. So this is just a way to convert intensity to decibels. This is how the decibel is defined, actually. So let's look at some examples of how many decibels you would get for a given intensity. So if beta equals 0 decibels, that implies that the log, so who knows how to invert logs? Well, you could raise both sides to the, or you could take both sides, raise it to the 10th power, or take 10, raise it to the both sides power, and so on. But we know that log base 10 of 1 equals 0, right? So that just means that that I divided by I naught has to be 1. So this implies that the intensity associated with 0 decibels is the reference intensity. So that means that according to our scale, 0 decibels is the quietest thing a human can hear. Can't hear less than that. Negative decibels would be less intense. It wouldn't be like negative volume. It'd be like 10 to the minus 13, 10 to the minus 14, and so on. We can also look at 120 decibels. 120 decibels, well, we know that that means, so we have 10 decibels. Let's just drop units. 120 equals 10 times log base 10 of I over I naught. So what does this mean? That means that I has to be 10 to the 12 times I naught, right? Because then you'll just get log base 10 of 10 to the 12th multiplied, log base 10 of 10 to the 12th is just 12 multiplied by 10, and you get 120. So that would mean that I is equal to 1 watt per square meter. This is the threshold for pain. So at 120 decibels, the thing that you're hearing is going to make your ears hurt. But we could keep going with this game. If we take beta is 278 decibels, that gives you an I of 6.3 times 10 to the 15th watts per square meter. That's approximately 13 orders of magnitude, or 15 orders of magnitude higher than the threshold for pain. In fact, this is the volume of a nuclear bomb. It's the volume of a nuclear bomb. And if you experience a sound that loud, you are dead. Because it's a very, very high pressure wave. Like the amplitude of the pressure wave is very, 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 very high. And it would rip your organs to bits and probably vaporize you. So the point is even though we went up 120 decibels to go from quietest sound to pain, there's clearly a bigger difference between dead and pain than there is between pain and can barely hear it, right? So this is a logarithmic scale. And this says something about the way that we hear sounds, right? If something is 40 decibels and another thing is 50 decibels, it doesn't sound, or let's say 40 decibels and 60 decibels, right? That's like a quiet conversation versus like a highway. That's a difference of 20 decibels, which doesn't seem like a whole lot. However, the intensity is different by a factor of 100. So we don't, even though the intensity differs by a factor of 100, we detect it as being like a change, but not a significant change. It's not increasing the volume by a factor of 100, it's increasing it by maybe 50%. It just says something about the way that we hear. So just a quick reminder, the intensity is proportional to the amplitude squared. It's also proportional to the distance away from the source squared, right? So that is to say, if you say you have a source producing sound, right? If you double the distance but keep the amplitude, but keep the original amplitude, let's call this A naught, but keep the original amplitude the same, then it will get, the intensity will drop by a factor of 4. If you double the original amplitude but stay the same distance away, the intensity will increase by a factor of 4. So, in particular, if A doubles and R doubles, I stays the same. And so hence you would have the same volume, the same number of decibels. By the way, when I say volume, I'm actually referring to the measure in decibels. So, okay, great. We've talked about decibels. By the way, that will help you with question 5, I want to say, on the homework. Maybe it's question 6. No, it's question 5. It's just a matter of relating intensity to distance and using how intensity relates to decibels. So we're going to change gears a little bit to answer questions 6 and 7, basically. What we're going to talk about is what happens. Are we already 3 pages in? No, we're only 2 pages in. What happens when the speaker or listener or both is moving? Let me move this down a little bit so I can put a page break. There's 6 pages, or 5 pages. But I think we're making good time. We're 2 pages in, we're about 37 minutes in. So we're actually probably gonna finish just a smidge early. So we'll be fine, don't worry. So the way that we answer this question is well, we have to characterize something new, right? We haven't talked about what happens when a source is moving, because that's a new phenomenon. Turns out the first guy to, I guess, mathematically or empirically characterize this thing was a guy named Doppler. I don't remember his first name. And so he got his name attached to this phenomenon known as the Doppler effect. So this type of effect occurs for all waves. But light and gravity are a bit different. So there is still a Doppler effect for light waves and gravitational waves. However, the mathematical characterization is a little bit different. And that's for good reasons, but reasons that are above your heads. So we're not going to get into why they're different, but I will give you the formula. However, for sound, we can just characterize it directly, and we can actually derive the result. So let's talk about the Doppler effect for sound. Come on, scroll. There we go. So what we're talking about here is, imagine that you have like a speaker or like a loudspeaker. Say it's on a car and it's driving along. Well, what happens to somebody that's listening to that loudspeaker as it moves? Or similarly, let's say that you are in a car and you're listening to another object, to a speaker that's stationary, and you are moving with respect to it. What do you hear? That's what we're trying to understand. So when the source is stationary, sound is emitted radially outwards. So all the pictures I'm going to draw, by the way, are 2D, but they're just 2D representations of like a 3D thing. So let me show you an animation really quick. I think it's this one. Yeah, so just imagine that black dot in the middle is a source. It's emitting sound waves, and they go in all directions, perfectly spherical. In this case, they're circular because it's 2D, but imagine that it's emitting spherical waves. That's all that's happening. The distance between any 2 wavefronts is always the same. That's important, right? This is completely intuitive. We're going to change things up a little bit. So sorry. So what we want to know is, or what we can ask about a stationary source is, how does the observed frequency depend on the distance between crests? Well, it actually should be fairly straightforward, right? So let me, I could either pull something up or I could just draw it for you. I'm trying to decide how challenging it would be to draw. I actually have these PDFs already online, so I'll just show you. I'll just show it to you. I'll just show you the PDFs. So here we have a source, stationary, and a listener, also stationary. So just as before, just as in the animation, the source is just emitting radially outwards in these spheres. And so if, say, the frequency is, say, 5 hertz, that means that there are 5 cycles per 1 second. So how many crests would it send out in a period, or how long would it take to send out a single crest? It'd take 0.2 seconds. That's the period. Further, we know that the sound wave speed depends only on the medium in which the sound is propagating, right? That's just a property of waves. So the speed v is just the same. So the question is how is the how do you get the period, i.e. the duration that the how do you get the wavelength of the like if you're just a stationary listener, you can't get out a measuring stick. How do you get the wavelength from the from what you observe? All you observe is you hear crests coming every certain amount of time. That's the period. Well, if you want to calculate the wavelength, what you need to do is you need to take your period, multiply it by your wave speed, and you get the wavelength back. And that's a way that you can get the wavelength from the period. Similarly, if you knew the wavelength and you knew the wave speed, you could compute the period by dividing the wavelength by the speed. So this seems obvious, and it kind of is, but things are going to change in a minute, and so I just wanted to indicate how these quantities can be related to each other. Now let's go back to the lecture really quick. Gonna ask a few more interesting questions. Oh no. Wait a minute, which one's next? Oh boy, it's frozen. Unfreeze. One of my gifts, sorry guys. Oh, I'm frozen too. I think I'm lagging. Hope my machine didn't just crash, but I don't think that you can hear me anymore. Let me see if I can fix this. Oh, hey, I can see myself. All right, I'm back. I'm back. Can you guys hear me? Why can I hear myself twice? Oh, because I actually don't know why. Why can't I hear myself? Why can I hear? Okay, I think we're good. I need to leave the Zoom meeting on my other PC. That would explain it. All right, much better. Okay, let's get back to business. Can everybody see me? Everybody hear me all right? Sorry for the technical difficulties. All right, let's get right back in. Share screen. All right, I'm gonna stop flitting between the two things. I will just draw pictures. It'll be a little bit easier. I'll just have to reference the my other screen so that I can draw them properly. Let me put this over here like I usually do. I just lost it. Today's recording might be up late because I will have to combine the recording that happened before the disconnect occurred and the recording that happened afterwards. This happened before, it happened last quarter. It was really annoying when it happened, and it took like 2 hours to actually combine the videos, so sorry about that. It'll probably be delayed, and then I have a meeting, so. Well, I have office hours anyway. It'll come out later tonight, though. Anyway, let's jump right back in. So we already established how the observed frequency depends on the distance between the crests. Lambda is the distance between the crests. And so v is the wave speed. It's called Vs. Wave speed. And so the period is literally, just the period that the listener observes, i.e. the amount of time between crests that the listener observes is just lambda divided by v. Easy peasy, right? All right, things are now going to get more complicated. So what happens if the listener moves towards or away from the source? And I'm going to do my best to draw this, so please bear with me. By the way, the things that I'm drawing, you can find them on Canvas, so if you want to reference them, now's the time. Oh, let me invert this. There we go, much better. So let me do my best to draw it. So we have our standard circles. Oh God, that's terrible. Oh boy, this is going to be rough. All right, so here's our source. This source sends out a period, or sorry, sends out a crest once every t sub s seconds. That's the period as observed from the reference frame of the source. Now, the wavelength, this distance here, wavelength is just as before. It is just lambda, which is v times t sub s, right? Nothing changes there. The wavelength is the same. Now, the wave speed is just determined by the medium, so it's just 344 meters per second. Now, instead of what we had before, where we just had a stationary source, stationary listener, now our listener is moving with some speed, say VL. So what is the period that the listener notices? Oh, let me move that cable. So the period that the listener notices, TL, period for the listener, this is the amount of time between crests. This is equal to the wavelength of the wave divided by the apparent speed of the wave. So the speed of the wave, so the wavelength is just the wavelength. If this person got out a ruler, they would measure the appropriate distance between the waves. However, what's different here is that because the listener is going towards the waves, it looks like the waves from the listener's perspective are moving faster. So the apparent speed of the waves is v plus VL, because the listener is moving towards the waves. So what is the frequency that the listener observes? Frequency is just 1 divided by period, which is just v plus VL divided by lambda. And we can rewrite that as 1 plus VL over V times V over lambda. Now V over lambda is just the frequency it's just the frequency that the source emits, right? So this is 1 plus VL over V times the frequency of the source. That is the frequency that the source observes. So the whole point here is that the observer and the source, or the listener and the source, both agree on the distance between the crests. However, they don't agree on the speed at which the wave travels, or the frequency, and that's because they don't agree on the speed at which the wave travels. So what ends up happening, and by the way, I'm going to rewrite this in terms of a more familiar term, a more familiar notation. This is V plus VL divided by V times Fs. This is the frequency of the listener. So what ends up happening is that because the waves appear to travel faster, we get that the frequency appears to be higher from the listener's perspective. And that's something that we notice, right? That like we hear this in real life. Like when an ambulance is driving towards you, the pitch is higher than when it's just stationary. That's something that we definitely notice, especially when it's going 60 miles an hour or whatever. Just one thing to point out here. VL is signed, meaning whether it's positive or negative matters. It's negative if moving away, if the listener is moving away. VL is negative. If moving away from or toward the source, then VL is positive. And that kind of makes sense, right? The relative speed, if VL is moving away, should be smaller than the wave speed. The apparent wave speed should be smaller than the standard wave speed if the listener is moving away. And similarly, it should be higher if the listener is moving towards. So what we find out is that we find out that if the listener experiences a higher wave speed than the standard, then you get that you get a higher listener frequency than the source's frequency, and vice versa. Now, you could say, well, what if the source is moving? Is it just the same? Not quite. It's almost the same. But here, you can't just say, oh, well, if the listener is moving, then that's the same as the source moving, because there is a reference medium here. The air is stationary, and we have to be talking about motion relative to the air. So, so we need to do a separate analysis here. What happens if the source is moving? Things do change. We're actually going to finish pretty early, I think. Yeah, that's okay. We'll finish early, and then I can go through some examples. Well, I'll go through some examples for this anyway. So let me open up another thing. Where is it? So for this, I actually need an animation, which is kind of annoying, but otherwise it's kind of not clear. Okay, I won't deal with an animation. Everybody, go on your phones. Oh, nope, it's starting up. You know what? I'm not going to deal with this, though, because I don't want it to crash again. So everybody, go on your phones, go to Canvas, and if you look under Files, you should see a file called moving source, or lecture3-moving source.gif. This is under lecture files on Canvas. If you go ahead and click on that, you can actually see the GIF that I'm talking about. So I'll just give you a few minutes to do so. And if you've already seen it, then go ahead and take a bio break or something. Yeah, so if you click on Files on the left-hand side of Canvas, and then you go to Lecture Files in the folder Lecture Files, then there should be a GIF called lecture3-moving source.gif. So the crest in the direction that is moving remains small. No, it actually gets smaller. That's the takeaway here. The crest, so if you wanted to look at like the normal crest size, it's not that the one in opposite the direction gets bigger, it's that the one opposite the direction of motion gets bigger and the one in the direction of motion gets smaller. There's actually both effects are taking place. If you looked at the distance between crests perpendicular, those are going to stay the same. I'll just give it till 11 o'clock before we continue, so everybody can take a look. 2 minutes seems to go by a lot longer when you're sitting in silence, huh? All right, I'm going to assume that everybody's taken a look at it. We'll just continue here. So we're going to try to analyze what happens after we turn in the homework. Will I provide the answer key? Yeah, there will be an answer, a set of answers provided. Right, so I'm going to draw out just a quick picture. Let's imagine that the source is moving towards the listener. So we have our source, draw a little dot here. And so, it's hard to draw. Something like that. So the source is moving with some speed, Vs, let's say. Oh, I should not have used Vs for the speed of sound. I'll just use V for the speed of sound. There we go, problem solved. Vs is the speed of the source, and V is the speed of the wave. The distance between each crest is lambda. That just is the difference between the crests from relative to the air. So we can compute that. So the distance between each crest, oh, and I'll put a listener over here. Well, if the source was not moving, it would just be lambda, we know, is just V times Ts, the time between crests being emitted by the source. However, we know that after a given amount of time Ts, the source will have moved a certain distance closer to the listener, so the next crest would be emitted closer. So what we want to do is we want to subtract off that extra distance. So we subtract off Vs times Ts. This is the distance traveled by the source between crest emissions. So in the time it takes for the source to emit one crest, it travels a certain distance because it's moving. And so if we want to compute the distance between each of those crests, we have to take that into account because now the next crest is emitted further along. So we can factor this. This is V minus Vs times Ts. And so what does the observer see? The observer sees waves moving, they're still moving at speed v, because the observer is not moving relative to the air, and the speed of a wave only depends on the medium. And wavelength, lambda, right? The wavelength, this lambda here. So what does that tell us? That tells us, that the frequency that the listener observes is V over lambda. That's always true, right? It's always true that frequency is V over lambda, but now lambda takes on a different form from what we're used to. So it's V over V minus Vs times Ts. So we can rewrite this. It takes a little bit of effort. Remember, 1 divided by Ts is just the frequency. So this is just equal to V divided by V minus Vs times F sub s. And again, we have to note that V sub s is signed. What do I mean? It means that the time between crests gets larger or smaller the distance between crests gets larger or smaller depending on the direction the source is moving. So we know that the distance between crests gets smaller if the source is moving in the same direction as the waves, or moving in the same direction towards the listener. If they're moving away from the listener, if they were moving instead to the right, then, or if the listener was over here, then the distance would get bigger because they cover more, because the next crest is emitted from further away. And so the fact that we have a minus here indicates that the source was moving towards the listener, but it could have been a plus if the source was moving away from the listener. So how do we account for that? Well, here we have a minus, or we get a negative sign. Negative sign when we have source moving towards the listener, and a positive sign when the source moves away. So let's just do a quick analysis here, just thinking about this. If the source is moving towards the listener, that means that the denominator gets smaller. V minus Vs is smaller than V, which means that the fraction V divided by V minus Vs is greater than 1. So we get, so the listener hears a higher frequency. Again, this is what we observe. This is actually what we observe with an ambulance, because the ambulance is the thing moving. If you were moving relative to an ambulance, you would observe the other effect. So what we see is that anytime two things, the source and the listener, their distance is getting smaller between them, we would see that the frequency goes up. Regardless of whether or not it's the listener or the source moving, you always get an increased frequency when the distance between two things gets smaller. Similarly, when the distance between two things gets larger, i.e. if you have a plus sign here instead of a minus sign, then that means that the source is getting further away, or the listener is moving away from the source. So when the distance between the two objects is getting bigger, that means that you have a lower frequency. You hear a lower frequency. And in fact, we can combine both of these effects, right? We can combine these two effects into the general Doppler effect. The way we do that is just by noting that if the listener is moving, it just changes the numerator, and if the source is moving, it just changes the denominator. And so the frequency that the listener hears is V plus or minus VL divided by V minus plus VS times F sub S. And now we have to be careful with this equation. We have to know when to use the positive and negative signs. For each of the signs, you choose the top sign for moving towards, and we use the bottom sign for moving away. So we have some time. So I'm just going. So this equation can be used in all cases. If one's moving towards and one's moving away, then you can combine it. And I'll do a quick example. But just as a quick way to remember, how do you spell mnemonic? M-N-E, mnemonic, I think. If they're moving towards, then the frequency of the listener should go up. If they're moving away, the frequency of the listener should go down. Basically, if the distance between the things is decreasing, then the frequency of the listener should go up if they're moving towards each other. If the distance between the objects is going up, then the frequency should go down. So let me just do a quick example, since I'm actually like almost out of material. I just have a little bit more to cover, and we have plenty of time. So let's just come up with some random example. So let's say that we have a speaker on a car, and a listener in another car. So we have our oh God, I always have to draw. I'm so terrible at drawing cars. You know what, I'm just gonna draw a speaker, and the speaker will be moving. And it has wheels. And then here's our listener. Our listener is a person. Now, there are a few different ways that we could, and they're wearing roller skates. There, now they're moving. So let's first analyze the most straightforward case. And by the way, keep in mind all of these speeds that we're talking about are relative to the stationary air. So let's say the speaker is rolling towards the listener, and the listener is rolling towards the speaker. Maybe we have a speed here. Maybe the speaker is rolling towards it at 10 meters per second, and the listener is rolling towards the speaker at 10 meters per second. Just make the numbers easy. Or actually, let's make it even easier. Let's do 6 meters per second. No, 4 meters per second here. Sorry, I'm trying to pick the numbers that make it easy. And 6 meters per second here. So they're net moving towards each other at 10 meters per second, but we do have to separate this. We have to say, how quickly are they moving relative to the air? That is important. So if, let's assume the speaker emits, let's say 1,000 hertz sound wave. Right, so it emits a crest every 1/1000th of a second. Keep in mind that the human ear can hear anywhere from 20 hertz once every 1/20th of a second to approximately 20,000 hertz. So this is kind of like smack dab in the middle in our hearing range. It's on the high end. The human voice is somewhere around 400 hertz or so, depending on how high your voice is. But you know, we can hear 1,000 hertz, and it'll make our math easier. So now the question is what does the listener hear? Well, let's plug it into our formula. So F sub L should be equal to, it's 344 meters per second. That's the speed of sound. That's the V that we use there. And now the listener affects the numerator. So the listener is moving towards the speaker at 6 meters per second. So we use the top sign, so we have plus 6 meters per second. And now we divide by 344 meters per second. And the speaker is moving towards the listener at 4 meters per second. So we choose the minus sign. So we have minus 4 meters per second. Perhaps now you can guess why I chose the numbers that I did. And then we want to multiply that by the speaker's frequency, which is 1,000 hertz. So we can do this math. It's relatively straightforward. It's 350 divided by 340 times 1,000 hertz. And now that's not some division that I can do in my head, so I will do it on a calculator instead. 350 divided by 340 is not straightforward. So it is, the listener would hear a frequency of about 1,029 hertz, which not a huge difference, but that's because the motion was slow. By the way, I should mention, if you are moving close to the speed of sound, lots of things go wrong. In particular, if the source is moving away from you at the speed of sound, you might not hear a whole lot. Or if they're moving toward, like how do I want to phrase this? If the source is moving towards you at the speed of sound, that means that you have a minus sign and Vs is equal to V. That would mean that you're dividing by 0. And that's because your frequency actually goes to infinity as you approach the sound barrier. And that's what a sonic boom is. It's when all of your wave fronts, when they all collect on top of each other because you're moving so quickly. just as a little aside. Let's do a slightly more complicated example. Let's say that our speaker is moving away at 6 meters per second, and the skater is still moving towards. That's the speed of sound, it's just a number. And let's say that the speaker is moving towards them at, towards the speaker at 16 meters per second. So now the gap is getting smaller by 10 meters per second, but it's due to different effects. If both persons, yes, that it would be essentially the stationary case. The stationary case would be precisely that. So let's look at this example. So here the gap still shrinks. At 10 meters per second, just as in the above example, but we'll see something different here. So now, and we're going to assume it's it's 1,000 hertz again. So now the frequency of the listener is 344 meters per second, and the listener is still traveling towards the speaker. So we have to add 16 meters per second. And now we have to divide, but the speaker is moving away from the listener. So we add 6 meters per second, and then multiply by 1,000 hertz. Okay, well, we can again do this. We have 360 divided by 350 times 1,000 hertz. It's just the speed of sound. It's just a number. I mentioned it way up at the very beginning of at the beginning of lecture. That is the number. It's the speed of sound in air at standard temperature and pressure. So that's the number that we plug in for v, because that is the speed at which the wave propagates. And that's where all these v's, those are the wave speeds, which is the speed of sound. So we can do this math again. 360 over 350. So this is approximately 1,028 hertz. So even though the gap is shrinking at the same rate, the frequency that the listener hears is different because the cause of that gap shrinking is different. It's just, it's a strange, well, I guess it's not that strange because it depends on the motion of the air as well. But so the frequency that you hear, I guess what I'm trying to get across, does not only care about the rate at which the gap is shrinking. It also depends on how quickly each individual part is moving, and that's because the speed of sound in air is fixed. And so if the speed of sound is fixed, so if the listener is moving, they experience a higher speed of sound or slower speed of sound. Whereas if the speaker is moving, it's a different effect. They change the wavelength. So if you increase the temperature, the density of the air will go down. If the density goes down, the speed of sound will go up. Yes, that is true. And in fact, lighter gases like helium tend to have much higher speeds of sound, whereas heavier gases have lower speeds of sound. And actually, that is why when you breathe in helium, your voice gets really high, because the period's still the same, but or rather, the wavelength is still the same, but the speed changes, so the frequency changes. Right, okay, so we have one more thing to cover. This will help you get through question 7. We have to talk about light. So I mentioned that the Doppler effect happens for light and sound and gravity waves, but I told you that it was more complicated for light. So for light, well, what we learned from Einstein is that light travels without a medium. Well, we didn't learn that from Einstein, we learned that from Michelson and Morley, but light travels without a medium. It doesn't need something to travel through. Or if you want to be pedantic, maybe you say it travels through space-time or something. It travels without a medium. So whatever happens when you're moving, it shouldn't depend on the motion of the medium because there is no medium that's moving. And further, it is observed, and Einstein proved why this is the case, the observed speed is always the same. So the example here is, imagine that, remember, a light wave is just an oscillation just as much, so it has peaks and troughs and stuff. So imagine that somebody sends out a light wave that has a peak every 1/10,000th of a second. You might imagine that if the listener is moving, going back up to this example, you might imagine that for light, they might also see that the light appears to be traveling faster. But what makes light and gravitational waves as well different is that light always appears to travel at the same rate. And you'll learn about why this is the case in 9D if you decide to take it, but this is an interesting phenomenon, and it's true. It doesn't matter how fast you're going, light will always seem to move at the same speed. This is the speed of light. It's something like 3 × 10⁸ meters per second. And so even if you were on a train moving at half the speed of light and you shined a flashlight outside, it would still appear to be moving at 3 × 10⁸ meters per second from your perspective. So that kind of throws a wrench in this whole idea that we had here, because the way we calculated the change in frequency for sound was we said, okay, well, look, the speed of sound appears to change because we're moving towards it, but that doesn't happen for light. So other phenomena instead happen. And so what we end up with is the formula for light, for the Doppler effect for light, is the following. It's the square root of c, which is the speed of light, plus or minus v, divided by the square root of c minus plus v, times the frequency of the source. And maybe I'll put observer, because you don't listen to light. And here you pick the top sign equals distance decreasing. And I'll explain this in a minute. And the bottom sign equals distance increasing. So, whereas in the case with sound, we had a listener speed and a source speed, here we don't have that. There's just c, speed of light, which is approximately equal to 3 × 10⁸ meters per second, very, very fast. And then v is the relative speed between the source and observer. Now, why is it that for the case of sound, we had two different speeds? We had the source's speed and the listener speed, but here we just have just the relative speed. Like, for example, if we were in this case, where but for sound, we would use 10 meters per second in both cases for v, because that is the relative speed between the two objects. So why is it that we only care about the relative speed here? Well, think about it a little bit carefully, and you'll realize that the reason why we had to use two different speeds here, and why the relative speed isn't the only thing that matters, is because there's a third speed involved, and that's the speed relative to the air. And the air, the speed at which you're moving relative to the air is the speed at which you measure the sound. But if there's no medium that you're measuring the speed relative to with regards to light, and if light always travels at the same speed regardless of how fast you're observing it at, the only speed that could matter would be the relative speed between the source or the emitter, as we would call it, and the observer. And so what we would say is, if the distance between two objects is, say, decreasing by 100 meters per second, you would plug in c plus 100 meters per second divided by c minus 100 meters per second. You'd choose the top sign in both cases because the distance is decreasing between them. So you choose plus in the numerator and negative in the denominator. If the speed is decreasing, if the distance between them is increasing, i.e. the speed, like they're going away from each other, you choose the negative sign. And so the same effect happens if the objects are getting closer together. You will observe a higher frequency of light. If the objects are getting further apart, you will observe a lower frequency of light. And just so you guys know, and we'll talk about this next week, I think, the frequency of light has to do with its color, effectively. Red is a lower frequency of light, blue is a higher frequency of light. So just like how we hear pitches, or just as how we hear frequency of sound as pitches, we see frequency of light as colors. So if something is traveling, there's an old physics joke that a physicist, maybe it's Albert Einstein, is speeding down the highway at half the speed of light. By the way, green is a higher frequency than red. So that's relevant for the joke. So Albert Einstein is speeding down the highway at half the speed of light in his car, and a cop pulls him over. And he runs a red light, and a cop pulls him over and says, "Professor Einstein, did you know that you just ran a red light?" And so Einstein says, but from my perspective, it was green. And it's a joke, and it's also informative, because Albert Einstein, or because the person driving, was moving very quickly towards the source of the light, the frequency goes up. And because green is a higher frequency than red, you can see why, perhaps from his perspective, the light indeed was green and was not red. Now, that probably wouldn't fly, because you probably shouldn't be going half the speed of light anyway on a highway or on a surface street. But, you know, it is what it is. Now, does some weird phenomena occur with light, similar to sound when the denominator approaches zero? So in order to get the denominator to, I will answer Grant's question, and then I'll comment on Seth's point. So the problem with, as the denominator approaches zero, what that means is that the source, or the distance between the two things, is getting is decreasing close to the speed of light. And you do get a weird bunching up of sound, or of light crests, but you can't actually get there, because that would involve the object, or that would involve the two objects getting closer at close to the speed of light, which is just not a thing. Like, you can't go the speed of light. There's no rules, or there's no way to break that rule. So you can't actually get. Actually, there's one exception. There's something called Cherenkov radiation. So the speed of light changes depending on what medium you're in. Just like how the speed of sound is different in air as it is in water as it is in steel, the speed of light is also different in different media. It's highest in a vacuum. That's where the 3 × 10⁸ meters per second comes from. However, in water, it's something like a third lower. So it might be like, it's 3/4 of the original speed. So it's like 2.33 times 10⁸ meters per second. So what can happen is you can have an object that is moving through the medium faster than light can travel through that medium. And that certainly does happen. And in fact, it happens in nuclear reactors quite frequently. When that happens, basically, you get a bunching up of light waves. And so you get very, very high or very, very intense bursts of radiation. And so when that happens, they're often ultraviolet or bright or violet or blue flashes, and this is called Cherenkov radiation. That's what happens when an object breaks the speed of light, or breaks the light barrier in a medium. And so you get these bursts of light, or these blue glows, and that is what the blue glow is when you're looking at a nuclear reactor, for example. It does not happen in a vacuum, because nothing can go faster than the speed of light in a vacuum. However, light does move slower than the speed of light when you're not in a vacuum. So indeed, it does happen. It's actually a really neat effect. I would suggest looking it up. It's called Cherenkov, named after some Russian physicist. Cherenkov, I think that's how you spell it, radiation. It's just really cool. Like, it looks like something out of a comic book. Sethu commented that it probably would have destroyed the entire highway. Kunsho, I'll answer your question in a second. So Sethu's point is a good point. In fact, there's a nice XKCD comic, or rather a what if blog post, about what would happen if a baseball pitcher threw a baseball at near the speed of light. And basically, it would destroy the entire city it was in, and possibly like the continent, because when things get to close to the speed of light, they have a crap ton of energy, like way more than anything that we've ever experienced. Like, we're talking nuclear bomb type energy, even for something as small as baseball. So, So Quenshow asks, is laser a bunching up of light? Yeah, was it actually the first what if? I wouldn't be surprised. It was a very good one, though. So a laser isn't a bunching up of light as much as it is just a stacking of light. So, a typical light bulb, and we'll talk about this. Oh, you know what's a bummer? My favorite part about teaching 9B when I've taught it in the past is that I have a big laser that I get to bring in and use it as a demo for the class. Oh, it's still on campus. I can probably it's my personal laser, so I can bring it wherever I want. But it's a nice demo, and it'll be hard to do over webcam. But maybe I'll do my best. But anyway, right? So a typical light bulb emits light like this, but it also emits light like this, and it's just like the waves are not in sync at all. Whereas for a laser, the waves are perfectly in sync. And so that's why you get the special phenomenon called coherence for lasers. And that's why they tend to be, that's not why they're bright, it's why they tend to stay in a straight line. Because they're in sync, they don't really spread out and decohere a whole lot. You also get this nice phenomenon of coherence for demonstrating double slit interference, which again we'll do next week. Right, so I guess we'll finish just a smidge early. Oh, just one thing I'd like to comment on. If the motion is not head-on, if the two objects are not going straight towards each other or straight away from each other or whatever, the Doppler effect gets more complicated. And in fact, in question 6, that's kind of what I'm asking you to explore. I'm kind of asking you to explore how that, like, I'm not asking you to derive anything. I just want you to think about it. Why is it that you hear a why do you hear a constant change in frequency when a car or an ambulance drives past you, as opposed to just a high frequency when it's coming towards you and a low frequency when it's going away from you? Why doesn't it go like why is it a constant change in frequency? That's what you're trying to analyze in question 6. It is complicated mathematically, but it's not really hard to understand conceptually. All right, so Grant, you're right on it. You got it. Don't give away too much, but that's basically it. Right. So that's all the lecture material I have for today. We did finish a little bit early, but that's okay. I think I'll probably tend to finish earlier because it's online. Takes less time to move around the room. So does anyone have questions that they want to ask? Because now's the time. I'm going to stop the recording, by the way.